So again, today we're gonna start with chapter 4. So let me share links now. Can you see it?
Yes.
Okay, so let me put it in full screen. Okay, so today, this is chapter 1 of Mascolel, okay? This is called Preference and Choice. I'm gonna introduce some additional new material at the end of the class about this chapter, but in general, we're gonna follow the chapter very closely at the beginning. So our objective right now, as I told you in the summer, is to model the center of any economic model, right? Which is a consumer decision maker. This decision maker is a human, right? So mostly, right now we have artificial intelligence as well, but initially we wanted to model human behavior in the context of economic interactions, right? So we want to model consumers right now, and to do so, we use preferences relations, which we cover in the summer. So this mathematical object called binary relation that we identify with preferences. We can also use utility functions. You know, this is the bread and butter of economic modeling. And we're going to learn today about way more about choice correspondences and choice functions in general, right? So which is the primitive of a theory. So we're trying to do science, right? So we are going to start from some primitive or something in principle observable that we want to understand deeper. What is the primitive of decision theory? Well, observed decisions, right? And how do we record these observed decisions? We're going to record them by means of what is called a choice rule or choice correspondence or choice function. I'm going to be clear about this in a second. But I just want you to imagine, so how if you tomorrow you say, I want to study choices and you want to reinvent decision theory, how will you collect this information? So let's fix examples, right? Say you want to understand choice under risk, okay? So you want to understand how people face risk, so how they choose when faced with risk. In particular, you're interested about attitudes towards risky prospects, right? So you are gonna offer them lotteries, right? And you want to understand, for instance, if consumers are risk-seeking or or they try to avoid risk, right? Or maybe they don't care about risk; they are risk-neutral, right? So, okay, that in the end is going to be my interest. I'm going a little bit ahead of what we're going to do today, but that's going to be a motivation for this class. So, right now, can someone tell me? I'm going to ask some of you to tell me, how can you collect data about that particular problem? So what would you do? So you become an experimenter, right? So you're given money by the Canadian, the social science council. They give you money so you can learn about risky behavior, risk attitudes. What would you do? Can maybe Yonkin tell me, what will you do to collect data about choice? So what kind of experiment will you run?
I think I will run some experiments similar to lottery or something in order to record the responses from my participants, like how they react when I offer them this kind of experiment. And I probably will tune in some parameters in my experiment. For example, like how much money I'm offering them in order to test. So I think that's going to be important. And what is the chance they go to the lottery? So through tuning this kind of parameters in order to test their sensitivity analysis, how they react to different settings, and to get my answers.
Okay, so thank you, Yonki. So I think it's a good answer. So let me tell you the simplest experiment we can run, and this is going to be the primitive of this particular chapter and of the class. So the simplest experiment is going to be to fix a choice set, right? So the universe of choices, right? So we are interested in thinking about risk in this particular example. So you can think of a collection of lotteries, right? So what is a lottery? It's going to describe the probability that you get certain price or amount of money in a given state of the world with the probability of such a state of the world. So imagine, for instance, that you have two states of the world, rainy and shiny, and I'm gonna pay you, for instance, $10 if it's shiny, and I'm gonna give you $0 if it's rainy. What's the probability of rainy and shiny? Is gonna be 50% each, right? They add up to 100. That's gonna be lottery one, right? Lottery two is gonna pay now $25 in the risky, sorry, in the shiny state, and $25 in the rainy, with the probabilities remain the same, right? So 50-50. Okay, so now you can also think of a third lottery, right? That is kind of the opposite of the first one. So pays money now on the opposite state of the world. Okay, so now think of so this is your choice set. Okay, how many items do I have there? 3. Okay, now Yonkin said, so I have to change something, right? So in an experiment, the experimenter varies something, right? To see how consumers react to this exogenous variation. So what is the main source of variation I'm going to study in decision theory? It's going to be availability variation. So that means I'm going to create from this grand choice set of 3 items, menus or choice sets of all possible subsets of these items. So in particular, out of 3, I can tell the consumers, my subjects, to face, for instance, lottery 1 versus lottery 2. And then in another round of the experiment, another trial, I'm gonna make them face lottery 2 versus lottery 3. And finally, in a third trial of the experiment, they're gonna face lottery 1 with lottery 3, okay? And then finally, I'm gonna give them all 3 lotteries together in the final trial of the experiment, okay? So this is called a choice. So this is called pretty much a choice set variation, okay? So I'm gonna vary the availability of items. So in the first trial, I remove lottery 3. In the second trial, I remove another lottery and so on until I had expanded all possible combinations of these elements in the choice set. Okay, so why do I do that? Why am I expecting to see? Well, I'm expecting consumers or subjects to pick something from these choices, okay? So imagine from lottery 1 versus lottery 2, I ask Schumann to tell me, which lottery do you like? So do you like the one that pays $50 in the shiny and 0 in the rainy versus 25 in either shines or rains? Which one do you prefer? Lottery 1 or lottery 2?
Lottery 1.
Okay, so lottery 1, that's a choice function, right? So he is picking from a choice set an item inside it, okay? So now if I ask Showman, do you like now lottery 2, which is $25, either shines or rains, versus lottery 3, which pays you $50 in the rainy stage. Which one do you like?
$25 the fun. $25.
Okay, so now he picked lottery 2. Okay, so now this again. So the description of all these things I recorded, and I'm gonna call that a choice function. Okay, so now what I'm trying to learn. Okay, so that's the important part. So I'm trying to learn the unobserved object, which is called preference. Okay. So, and this is what I'm gonna call revealed preference. So when Schulman told me in the second instance of trial that he likes lottery 2 over lottery 3, he's revealing to me that he prefers lottery 2 to lottery 3. Because even if lottery 3 is available to him, he picks lottery 2 over 3, okay? So he reveals to me by choice that he prefers, right, 2 to 3, okay? So when I'm learning this revealed preference information, then the role of decision theories is to try to find patterns on it, okay, and put laws on it. So I'm gonna tell Schumann is rational if he, for instance, satisfies this weak axiom of revealed preference, right? So if he tells me he likes first this lottery over this lottery, then whenever they are both available again, he's not gonna flip his alternative. So that's pretty much what I'm gonna do. Important things in real life, you know, in order for Schumann to actually choose meaningfully alternatives, he has to be incentivized to do so, right? So for instance, if he's choosing lotteries, a good experimenter will have to actually pay him according to the lotteries he's actually choosing. So he will get some money or tokens in an experiment given according to the description of the lottery, right? So the experimenter will flip a coin, and then if it's heads, it's gonna be rainy, right? And then I'm gonna pay Schumann according to that probability, okay, at the end of the experiment. So if he knows his choices are gonna have consequences, and actually monetary ones, he will be incentivized to choose truthfully if you want, okay? So then this is the kind of data we're imagining we have access to, right? Okay, so let's go and now understand this mathematically. So as you can see, we have here this object, which is what we're gonna call the choice set, which I told you is these 3 lotteries that we're imagining right now. In particular, this chapter is gonna be so general that this choice set can be anything really. So for instance, it can be commodity bundles, it can be vectors in the Euclidean space, can be lotteries, can be cars, can be donuts, whatever you imagine, right? So X right now has no restriction, can be anything you want. And then I'm gonna give you the primitive or the object of interest, so what is a data set? So, but before that, I'm gonna give you this description of choice, which is called the choice correspondence, okay? Now, choice correspondence is a mapping, so a mapping between what is written here is the power set. Okay, so 2 to the power of capital X means the power set of this big choice set. So this is in fact the collection of all possible subsets, including the empty and the universal set of X, okay? One thing I'm gonna remove from this is that I'm gonna remove emptiness. So empty here means this is the domain of this is gonna be the choices, the menus I'm giving the subject. So I'm never gonna offer the subjects no choice, right? So emptiness is removed. And this is mapping this support of choice sets to the image, which is a choice actually, right? And this here, notice that I'm allowing subjects to pick more than one stuff, one item. So this is the first complication for you to understand this. What Schumann did is, and I didn't give him any other choice, is he only choose one item out of the menu, right? Versus I never told him, look, you can actually choose 2, 1 or more, right? So now if I was allow him to that particular choice, he might tell me, for instance, from the alternative lottery 1, 2, 3, he may say, you know, I may pick between lottery 1 and 2, right? So I don't mind either. So if he says that, then he is in the world of choice correspondences. So the rule of thumb is this. Choice correspondence is when you can choose more than one item, or in the words of decision theories, when 1 or more items are choosable, okay? It doesn't mean that you actually choose them, chose them, right? It just means that they are choosable, okay? And choice function is when you can only pick one item out of the choice set, okay? So function is unique, choice correspondence is not unique. It's a set image, set value object. Now, so I kind of told you, you know, Schumann will tell me I can pick between 1 and 2, right? But in reality, it's very difficult for an experimenter to pay him if he does that, right? Because then how do I pay him across these two items? So he says, you know, I may choose between 1 and 2, the lottery is 1 and 2. Then how do I pay him? So in experiments, it's very difficult to actually observe choice correspondences, okay? So what we mean by that really is that experiments can be run multiple times. So for instance, I can go to Schumann and offer him first lottery 1 to 3 in trial 1, and then in trial 10, I repeat the same menu, 1 to 3. And then in the first trial, Schumann chose lottery 1. And then in trial 10, he now chose lottery 2. So if he does that, then you know, experimenters sometimes record that information as belonging to the choice correspondence, right? So that means that a choice correspondence is kind of the union or the accumulation of all choices you did from a choice set. Maybe it was collected in time in many trials, right? So here we're eliminating any information about timing, right? So this is a summary of all trials that I did, and I collected this information. And there is no information as well about the frequency. So for instance, if I offer Schumann 10 times the same menu, 1, 2, 3, and half of the time he chose lottery 1, and half of the time he chose lottery 2, in the choice correspondence world, I'm eliminated that information. So I ignore completely the frequency. I only care about the support. So what things did he choose? So if he chose 1 time lottery 1 and 9 times lottery 2, I don't care. Both things are in the choice correspondence, okay?
So Victor, can you tell the more choices you give me or the more trials, the better you can model my choice behavior, something like this?
Okay, so that's a cool question, because one will guess that if you're choosing more often, maybe we can learn something else, right? But you have to really situate yourself in the context, historical context of this chapter, right? So this is, Samuelson Arrow's world. So they didn't have good data, right? So they are imagining very, very poor data sets where the experimentalists struggle to collect one choice out of a menu, right? So this is the kind of information we're dealing with right now. This is we are eliminating, we don't have that information right now. Even if we have it, we think is not useful. So we're not gonna use much this. Now, in reality, and that's why I'm going to introduce after this chapter a stochastic choice, and then what Schumann is saying will matter, because the more times I see you choosing, I'm going to have a better estimate of what is called the stochastic choice correspondence, which actually tells you the frequency of choices. So for instance, in the case of the example with Schumann, he will have 50% of the time choosing lottery 1, 50% of the time choosing lottery 2, okay? So that frequency is better estimated, of course, when you have more choices, right? But right now, in this stage, in this chapter, that information is completely disregarded because we don't have it, okay? So remember the historical context, right? This is poor man's data, but it's also very robust in a way, okay? This always works, even if you have really, really bad data, okay? Good, so,
sorry, I have a question.
yes, Rosanna.
So regardless of the frequency, is Schumann's choices still going to be weighted by the number of times he chose? Is it going to be 90% one choice, 10% another choice, or is it going to be 50-50?
So the interesting thing about choice correspondences is that they are non-deterministic, because you don't know what the consumer will pick, but they are not stochastic. So any information about frequencies is completely eliminated. It doesn't exist.
Wow.
Okay. So right now, choice correspondences have that feature, quote unquote. The frequency is disregarded. So when they are ideal is when you are a poor experimenter, right? Or your subjects are lazy and they will choose you cannot put a human with 1,000 times a menu, you see? So people do get this data, stochastic choice data, true stochastic choice data for individuals, for monkeys, for frogs. They do it, right? You can imagine, why. Because humans, it will be very difficult for people to face the same menu 100 times, 1,000 times, you see? So that's why we use choice correspondences, right? Choice correspondences, you can use 2 trials out of each menu, okay? Got it? Okay. Good. So now, so important thing. X may be infinite, right? So what is example of a choice that is infinite? So we studied one in the summer. So is the collection of all choice commodity bundles, right? Commodity bundles are elements, are vectors of the Euclidean space. So the Euclidean space is an infinite set, right? So you have infinite many bundles, okay? So maybe you don't have access to all possible subsets of these set of bundles. So in particular, for what we study in the summer, you realize that observers only have access to choices out from budget sets. So linear budget sets, remember? So for instance, in the consumer problem in the summer, you never saw consumers picking for a weird budget that was triangular shape, right? Or another circular one. That thing didn't exist in my data set. So right now, what I'm telling you is that usually the choice correspondence can be observed in a subset of the power set. So in particular, you will have something that is called the collection of menus, which is this calligraphic B, okay? And this is nothing else than a collection of menus. So one example from the set of lotteries, for instance, is the one I described. So imagine X is finite, you have 3 lotteries. So then I call my collection of menus of the calligraphic B as all items of binary sets, A, B, so lottery 1, lottery 2, 3, and 1 and 3, and the trinary menu, so ABC, okay? And that particular one doesn't have, for instance, the singleton menus, right? So those are not included. So the power set is not there, right? This is a smaller than the power set. Do you understand? So in particular, this calligraphic B is always is a collection of menus. And in simple words, this is what the experimenter can afford or the econometrician can observe, right? So imagine, for instance, I have money only for 10 trials. So even if I have a lot of potential commodity bundles, I can only run 10 experiments, right? So the 10 experiments will correspond to a choice set each, and this will be my calligraphic B, okay? So the collection of menus. Got it? Now, the choice structure is going to be, of course, the restriction of the choice correspondence to these observed data, so the observed menus, and therefore this is going to tell me the description of choices for my observed collection of menus. So in other words, I run my experiment 10 times. I record in calligraphic V the menu, and in C, I'm going to record what people choose. Okay, got it? So now, at this point, I'm going to do a small example, right? So we fix ideas. So it's not only theoretical, right? So again, so we have 3 lotteries, right? Lottery 1, lottery 2, lottery 3. An example of this collection of menus versus I will do even a simpler one. It's going to be, for instance, the collection of L1, L2, and L1, L2, L3. Okay? Only two menus, nothing more. And then the choices out of this thing will be the following. L1, L2. The choices out of this will be L1. So this is a singleton, a choice function. And out of L1, L2, L3, this consumer in particular will now choose L2. Okay? And this is a data set, okay? This is a data set. Now, of course, let's say now that I have a choice correspondence just to make it more complicated. So this will be a choice correspondence, right? L2, L3 in the second instance. So I don't have to have the whole the power set. I can have only a subset of the menus, and then I have to have the descriptions of what people are choosing out of it.
Sorry, just a clarification. Yes. The part where you're doing the choice between L1, L2, L3, why in that case there's a choice of 2 lotteries? Like, do we have any restrictions of like if you're choosing 1, 2? Like, how do you know in that case?
No, this is a complete invention by. So I'm an experimenter. I'm choosing this particular menu. So there is nothing deep about it. It's just an example, right?
Okay.
Yeah. Now I want to ask you a question. So you remember what is a rational consumer, right? So rational is transitive and complete, right? So now you're an experimental, you collected this data, right? And now I'm gonna ask you the following question. So can this data be generated by a rational consumer? Do you understand what I'm asking? So,
No.
so Hursana already says no. So can you tell us why, and then we can go deeper into the question. Yeah.
So because when the consumer had the choice between L1 and L2, they chose L1, but then in the second set, L1 was still present, but they didn't choose it. They chose L2 and L2 over L1. So these two, it's not transitive.
Great. So there is obviously something weird about these choices, right? So Hursana detected this. This consumer is flipping their choices, right? So first they like L1 strictly when L2 is present, and then L1 is available to them, but now they pick L1.
Victor.
Sorry, L2. So they actually are breaking this consistency, right? So in particular, you know that this, this will break transitivity and completeness, rationality in general, right? So,
sorry, I just have a question about that.
Yep.
Is it possible that this could still be a rational consumer, say if L2 and L3 are complements, and perhaps the consumer prefers those two, but since only one of the two was offered in the first menu, then they chose L1 because it's consumable alone?
Okay, now that's a great question and a great comment, but I want you to realize something. So Evan said, is it possible that they are still rational, right? So I can rephrase it and say, is it possible they are still smart, right? Intelligent? And there is a deeper reason why they actually change their choices in such a way. And now suddenly there's some level of complementarity, right? And this is something famous called the attraction effect, right? So when you introduce this item L3, when it was not before, this acts as a decoy for L2, making it more attractive now, right? And now suddenly this consumer, because its attention or perception is changing now, they will give bigger weight to L2 and L3. However, this is not rational for us in this class because rational is transitive and complete. These preferences can never be compatibilized with, they're not compatible with transitive and complete, right? So these, in other words, these complex interactions between attention, complementarity of attention, and so on cannot be modeled by transitive and complete consumers. Transitive and complete consumers are very simple consumers. Remember that transitive and complete means that you can rank everything and put it in a single line, the real line, right? So therefore, complex things such as complementarity will need another axis, right? So they cannot be covered by this. So now, what Evan said is correct if I rephrase his statement about them, this consumer being rational by this consumer being intelligent. So of course, this doesn't rule out that they are still smart and this choice is motivated by insightful reflection, right? But it's not rational, okay? So that's the cool thing, right? So we have a theory and we can test it. We know it's not rational. But now let's go deeper into that. I'm going to formalize what I ask you, is this rationalizable? Now I'm going to tell you mathematically what that is, right? So
ruling out a convex combination
yes.
of the lotteries? Are we ruling out any convex combination of the lotteries, right?
So right now, I'm not assuming anything about convex combinations. So this is a very simple finite choice set, and I have two finite menus from it. Here, I'm not assuming existence of any convex combination or anything, right? So super simple. Okay, so what does it mean to be rationalizable? So remember, C is data, right? So small c is the choice correspondence. And I say this object is rationalizable when this set here, for any choice set A, is equal or equivalent in the set sense. So what does it mean to be equal in the set sense? That this set here is quickly contained on this other set here, which is the C star of the preference relation. But also this set here on the right is contained on the CA, right? So together, the containment relation, containment of sets is also a relation, a binary relation. So the equivalence relation of that is that containment goes in two ways, okay? So two things here. From order theory, we know that the containment relation in the sets, in the space of sets, is a binary relation. And the equivalence relation related to the containment thing means that the containment goes in both directions, right? Everyone agrees? Okay, so this is the equivalence relation here. And so what I'm saying is, in fact, that I can always generate the data in the left-hand side where the cursor is, from a model. And this particular model in the right-hand side is coming from a transitive and complete relation, okay? So in particular, that's the cool thing, right? I can take data and I can generate a model, which is the preference relation here, that will reproduce exactly the data I'm seeing, okay? That means being rationalized, okay? Everyone understands? Okay, so a parenthesis. So you know what is an OLS model, a linear regression, right? Ordinary linear squares, okay? So what is the data usually there? So imagine a simple, single scatter plot of quantities and prices. So this is your data, right? So these are points, mapping prices to consumption, okay? Now, your objective is to fit a model, right? So you want to fit a line. Imagine they actually align, and so you can actually perfectly fit a line. And this line has two parameters, right? An intercept and slope, okay? So given the data set that you had, you're gonna find the particular intercept and the particular slope that exactly reproduces the data. Okay, so this is more than ordinary linear squares, this is more like interpolation, right? So who is an engineer here? They will be more familiar with the interpolation, right? But I want a line that passes through the points, okay? And I found the slope and the intercept that achieves that particular objective, okay? So what is the intercept and the slope here? Is the preference relation, right? That's the parameter that you are feeding to the data, okay? But this parameter is way more complicated than the intercept and slope, okay? The binary relation, is a big object. It's bigger in dimension than an intercept and a slope, right? So it's actually a very deep parameter. So how do you conceptualize this? So we know already from the summer that I can write sometimes for continuous preferences, I can write utility functions that are the same effectively than using a preference relation, right? So what I'm asking you is in fact to find a function, a whole function, right? To explain the data. So it's not longer, a straight line with two parameters, intercept and slope. I'm actually asking to find a whole function to explain the data. Do you get it? So this is actually a high dimensional parameter I'm looking for. Okay, so preference relation are high dimensional parameters. I'm looking to explain the data. But the exercise is the same as in interpolation and in ordinary least squares. The data here is the data coming from experiments that is encapsulated in the choice correspondence. Got it? And then the model or the parameter I'm trying to exactly fit, here there is no noise, so it's exactly fit to the data, is the preference relation. Got it? This is what I'm doing. So it's the same exercise as in interpolation. Okay, so now everyone got it? Everyone's fine? Okay, so remember.
Can you just clarify once again what the meaning of the C star notation here is?
Yes. So here we have a triple equivalence. So we're now gonna focus on this second right-hand side equivalence, right? So the C star is the subset of the choice set. So all the items in the choice set that are such that are at the top of the ranking according to the preference relation. So these are the set of maximizers in this particular menu according to the preference relation that we're using. So this is just the collection of maximizers. So the key thing, another way to describe it, is that all items here are never dominated by all other objects inside the menu, okay? So you're never dominated, okay? This is exactly the same as being the elements at the top because my preferences are complete, okay? Under completeness, these two descriptions are equivalent, okay? Everyone got it? Okay, so this is the C star. So remember, C star is like the M and the intercept and the slope, okay? And the C without the star is data. These are points, okay? Information gathered by the experimenter. Got it? So with a star model, without the star data, okay? Now, again, we learned this in the summer, but we're gonna refresh it. Okay, so binary relation is a subset of the Cartesian product, right? So binary relation is this collection of ordered pairs, okay? We have the asymmetric part of it is, we say we're going to identify as a structure prefer A to B if A is in relation with B, but B is not in relation with A. And we're in the equivalence relation or indifference relation if A is in relation with B and also B is in relation with A, okay? Got it. So now this is an example of a proof we're gonna skip. I'm just gonna state the result. This is very easy, so I'm not gonna spend my time here. So first result in Mas-Colel is that if your preference is rational, then your asymmetric part is going to be irreflexive and transitive. Okay, so you can prove it to practice. We're going to use it in the class, so I'm going to state it now. This is very easy to prove, and it's a good practice to learn to do proofs. The second part is that the indifference relation is reflexive, transitive, and symmetric. Okay, and that basically means that you are in equivalence relation, right? And finally, it also tells you that the strictness is inherent in transitive chains. So if X is strictly preferred to Y and Y is weakly preferred to Z, then I conclude by transitivity combined with this information about the strictness that X is in strict relation with Z, okay? So now you can prove these things, but now we're just gonna use them. So this is a proof that is of course a study Mas-Colel. I have done it in previous classes, but right now I have new results, so I don't have time to cover it. But I encourage you to check it if you are not familiar with mathematical proofs, okay? Now, we're gonna do a quick detour, a little bit following Mas-Colel about talking about rationality. Right now, times have changed a lot. So we're gonna spend way more time talking about violations of the tenets of rationality later on with more depth than Mas-Colel, right? So the time Mas-Colel was teaching this, behavioral economics was a footnote, right? Right now is completely different. So behavioral economics is growing. People know that in most data sets, rationality doesn't explain data. So we have to reformulate and expand our toolset. But at this stage for Mas-Colel, it was just more like a curiosity, right? So he has this small, almost footnote about violations of transitivity, okay? So I'm just gonna tell you that, in fact, we're not studying rationality, meaning completeness and transitivity, because we think it's a complete description of human behavior, but we're studying it first because of tradition, right? It's very hard to remove tradition from any field. But second, because it's a very nice minimal model that we can learn the structure and we can learn to think about this problem as a decision theorist. And then we can easily expand these tools and this way of thinking to more complex models, okay? And this is the approach I take. But however, we have to acknowledge that this model is imperfect. So transitivity, in fact, is the problematic, is one of the problematic, is the main problematic assumption, I would say. Because completeness is conceptually weird. Because completeness requires that you can rank any two objects, right? If you have 3 items in your choice set, well, it's not crazy to require people to be able to rank these objects, because there are only 3. But if you have 100 objects, 1,000 objects, is it reasonable to ask consumers to be able to rank any pair in this collection of 1,000 items? Well, it's not likely, right? But it turns out that completeness empirically is not really important because you cannot really test it. It's very complex to test it. Imagine an infinite set. You can never offer this consumer all possible pairs, right? So in general, it's very complex to really find violations of completeness. Transitivity is the one that is meaningful. So rationality really is about transitivity. And so if you have issues with rationalities, they are going to be mostly about transitivity. And the first thing that we are going to acknowledge of problems with transitivity in real life is something that is called just perceptible differences. Again, all of this is kind of a wink to behavioral econ that we're going to take a deeper look later in more serious chapters about behavioral econ. But right now, just bear with it. Just perceptible differences, if you read the Mas-Colel chapter, they have an example about colors, right? And this example tells you, look, I am a painter. I'm offering you to paint your house, okay? And I'm offering, you know, this gamma of colors, and you know, you have different shades of blue. You have blue number 1 to blue number 20. If I give you options, right, from blue 1 to blue 2, most people are, I'm gonna be here, you know, the example, I cannot tell the difference, right? So I recently went with my wife to pick colors from painting a room. She was able to tell the difference between 2 yellows. I was not able to, right? So yellow number 1 and yellow number 2, for me, they are the same. If they give me yellow number 2 and 3, same. Yellow number 99 and yellow number 100 is the same. So it turns out that if someone is recording my preferences, right, then they will conclude that I'm indifferent between all yellows, okay? But, you know, my wife says, you know, it's just about that he cannot tell the difference. But what about if I show him yellow number 1 and yellow number 100, okay? These are now perceptible. The difference become perceptible. So now I see them, I see the difference. Finally, I see that they are different yellows. And then I say, look, this is too yellow. So 100 is too much for me. I want the 1. So now my preferences suddenly say, I prefer, you know, yellow number 1 to 100. So this is a strict preferences. And, you know, previously I was saying I was indifferent among all of them. And now I'm saying, I like strictly 1 to 100. So this violates, of course, rationality. It's very similar to the example that I created in class just before. So this is called just perceptible differences, okay? And, you know, this is an issue in general. For instance, you go to Costco, right? And you can buy, for instance, you go and buy these bags of chips or candy, right? And one of them has M&M and another doesn't have M&M. If you don't care much about M&M, maybe you don't see the difference much, right? Maybe one has better value, but you cannot really tell the difference, right? But if someone, you know, tells you this one has no chocolate and this one has for sure chocolate, maybe you can tell the difference. So this happens in many situations. You know, this is what it means to be just perceptible differences. If you fail to really see the difference among alternatives, you will fail transitivity, okay? First example. The second one is called inattention or misperception. That's very general here, but in particular, in the time of Mascolel, this idea wasn't really well formed. Now we actually understand what's going on. And the one thing that destroys transitivity is what is called lack of awareness of all your alternatives, okay? So in particular, for instance, imagine that that right now you go to the market to buy headphones, right? And so you go to Amazon, and then what do you do? So what do you do when you're purchasing from Amazon? So you're a grad student, you're busy studying, right? So you don't have much time to research. Or maybe you do, maybe you're already a researcher, so maybe you're gonna do it, right? But I'm not gonna talk about the ones that are investing too much time thinking about this problem. I'm going to talk about someone that doesn't want to think about this problem. So what do? You go, you open the Amazon, you search headphones, right? And then you start looking at the options that appear in the search results, the first 3, the first 4, right? And then what about the 5th one? You don't care. What about the second page of search? So who usually goes to the second page of Google search? Among you, many, I guess, because yeah, you're researchers, there is selection. But most people don't go to the second one, right? That's a fact of life, and that's called a consideration set, okay? So that means that most people don't consider all alternatives, right? You go to Costco, to Walmart, to Sobeys, to whatever you go, and then if you are in a hurry, you will check the items that are at the beginning of the shelf, right? So who checks the last corner, right? The very bottom one. Some people do, I know people, right? But most people don't. And that's another example of consideration sets. Okay, so now, what happens in consideration? Why this destroys transitivity? Okay, so then, you know, you may have issues like the one in the example where, for instance, having too many alternatives will make people to stop choosing, right? Or to suddenly pick something that is outside. So transitivity only works if you, in fact, are considering every alternative. So we're going to check these examples with more care later, but one implicit assumption in rationality is that the consumer is fully aware of all alternatives given to him by the experimenter or by real life in the menu. So part of the construct called rationality is that you are aware of every alternative in the menu, okay? If you're not, then transitivity may fail, but it doesn't fail because your preferences are not rational. Here they fail simply because the observer doesn't see the true choices, you see, okay? So, okay, this I'm gonna tell you with actual care later on. Right now for Mascolel, it was just, you know, something footnote. Framing effects, okay? So what about framing effects? So framing is a very big word in econ, right? So it's just about how I ask the questions, so the presentation of the questions, the description of the questions. So why this is weird? So another implicit assumption in rationality is that a choice is purely consequentialist. So who knows what means that choice is consequentialist? Or what do you guess it means? So can you tell me, Yoshiki, maybe? So when I say choice is consequentialist, what comes to your mind?
Well, agents only care about consequences.
Yeah, so
not like
perfect, right? So if you are in the experiment, as I told Schumann, right, he will only care about the monetary price he gets out from the experiment, right? He will only care about the utility he will get from the experiment. His utility only depends on the money he gets from the experiment, okay? Now, I'm gonna tell you an experiment I ran in Amazon Turk, right? So who knows what is Amazon Turk? Yeah, Kursana knows, right? So this, can you tell us a bit quickly?
So MTurk is basically a pool of people who volunteer to participate in surveys for small incentives, sometimes like $1 a question. And researchers usually use this platform to conduct online surveys.
Yeah, perfect, Kursana. So yeah, it's basically a platform for hiring workers, and you can hire them to do different tasks. And in particular, you can make them do decision tasks, right? And the cool thing is that you can actually pay a small amount of money for small tasks, and you can collect a lot of data, right? So in fact, I ran a risk experiment, right? An experiment about risk. So I offered them lotteries, and you know, the money they earn depends on the choices they make. So they depend on the lottery. Okay, so if they are consequentialists, their choices should depend only on the amount of money they get. However, my experiment had a twist, and it was that the presentation of the menus involved some cognitive task. So that means you, in order to understand the lottery, you had to solve some arithmetic operations. So, for instance, remember the lottery I offered to Schumann, $50 in the shiny state versus 0 in the other. Instead of telling him $50, I told him, oh, look, you will get 10 plus 10 plus 10 plus 10 plus 10, right? Of course, it's more complex than that, but you have to solve some operations, right? So of course, it's not gonna be as simple as that. So if you're an Amazon Turker, so you're working on that, you don't want to waste time, right? So you want to do this fast, get as much money as you want. So there is a cost of solving these problems, right? But this thing doesn't change the payment. It only changed the description of the problem, right? So decision theory assumes, and this chapter assumes, that there is no cost to understand the alternatives. So perception of the alternatives and understanding the alternatives is really perfect. So you don't have any emotional attachment or any cognitive barrier to understand the description of the alternative, okay? So in this particular case, framing comes in the form of a cognitive cost. So I make it hard for you to understand, and this changes frames exogenously, okay? So if you're a consequentialist, consumers will have to choose the same irrespective of the description. So what I did in my experiment was changing the difficulty of these arithmetic operations. So in a high cost or the difficult frame, I had 5 operations. In the medium frame, I had 3, and in the easy frame, I had 0, right? So consumers behave way more rationally when faced with a no cost or easy frame, right? And Another example of frame that is more common is when you add some emotions to the asking the question, right? So one classical example is, for instance, a loss aversion, okay? So people will change their answers according to whether you present the question as losing something or you present the questions in an opposite way as winning something. Even if the consequence is the same, the framing of wins versus losses changes the attitudes of consumers and therefore their choices. And the classical examples is Kahneman-Tversky, loss aversion experiments, where they give subjects the option of, right now we're in COVID time, so I can reframe it as, if you have a vaccine that has 10% side effects, bad side effects, right, but saves 90% of the population, right? That means, saves 90% and, has side effects of 10%. Would you choose, to go forward or to not go with the vaccine? So will you approve it? So a lot of people will say, I will approve it, okay? So remember that the choice here is, let's go with the vaccine forward. Now, imagine the same question with the same consequence framed as a loss. You say, if you go, so right now, if you go with the vaccine, 10% of the population will suffer and, lose their health, and 90% of the population will not, okay? So in this case, we know that the percent of people suffering and the percent of people not suffering is the same, right? But in the second one, you added emotion to it, right? You added a loss. So people are gonna lose their health, okay? So now, will you go with the vaccine forward? Most people say no, right? That's the loss aversion thing, right? So they change the risk attitude just because of the framing, okay? In the realm of losses, humans tend to be way more conservative. So if I ask you a question about losing, you will get way more risk averse. But if I ask you a question about winning, you will become risk lovers, okay? So that's, of course, that's the hypothesis of the loss aversion thing. But the important thing is that the consequence, if you're a robot, the consequences are the same. So both choices are exactly the same. If you like the vaccine in the first instance, you should like the vaccine in the second instance. But because emotions get into it, you're changing your choices, right? So that will break transitivity as well, okay? So another assumption here is, again, that frames are not important, right? So these are frame-free choices, okay? So that's another hidden assumption. And then another one, the final one, the Condorcet paradox. So Condorcet paradox is really cool because it's one of the first findings, logical experiment, thought experiments that came to kind of say transitivity is not that great. So the Marquis of Condorcet, a mathematician, also proto-economist in the French Revolution, he was very interested about studying how math can model society, right? And one of the things he discovered is all the issues that happens when instead of having one individual deciding, you have a group deciding. So it turns out when you have a group deciding, things get very weird, okay? So whenever you have more than one people choosing, then you lose transitivity, okay? So if for some reason you thought is being complete and transitive means actually that you're good at choosing, good quote unquote, right? This is a complete normative statement. There is no good and bad here. But if in the times of the Marquis of Condorcet, they actually thought being rational was something worth it, right? Worthwhile. So it turns out if you have a group of people choosing, you will lose transitivity, right? And this is one example. And so the example that I have, the one from Mascolelli, is the following. So you have a family, and then there are three options, right? You have a opera, a rock concert, and ice skating, okay? So O, R, and I. And the subscript in the preferences are the three members of the household. The first one is the mom, the second one is the dad, and the third one is the child, okay? So the mom likes opera to the rock concert and the rock concert to the ice skating. The dad likes the ice skating to the opera to the rock concert, and the kid likes the rock concert to the ice skating, to the opera, okay? Each of them has transitive preferences individually, right? But this household doesn't choose, doesn't have a dictator, right? So the household is democratic. It will choose by majority, okay? So when facing opera versus rock, who wins? By simple majority. Well, I just go and count votes, right? So the mom votes for opera, right? And the dad votes for opera, right? So opera wins. Now, rock versus ice skating. Easy, right? Rock wins. And finally, ice skating versus opera. Who wins? Well, the dad likes more ice skating, obviously, but the kid also likes more ice skating than opera, right? So now you have ice skating on the top. But then what happens, right? So we conclude, right, that the household likes opera to rock, rock to ice skating, right? But ice skating to opera, right? So now you have what is called a cycle, a violation of transitivity. Okay? So what does it matter? Why does this matter so actually today, right? So first of all, this opened a whole new field, right? Called social choice theory. Because, now, modeling society is different from modeling individuals, especially modeling how societies choose, like through elections. And there are a lot of impossibility theorems. It's very hard. So I don't do that, right? And it's too hard. I just deal with individual choices. But for us, we deal with data, real life data. And one data that people in the consumer empirics and consumer theory deal is with data coming from households. So I always talk about data coming from purchases from Walmart, from Costco, right? Retail shoppers. But who purchases at these Costco or Walmart places? Individuals or families? Well,
families, right?
Families mostly, right? So if you go to these data sets, it's almost 80-20, right? So 20% are single households, right? Which I love because we can model them with our models, right? And 80% are collectives, okay? And then, you have issues with transitivity, okay? So is all hope lost? Well, I hope that you don't get too disappointed, right? But the important thing is that we use the transitive consumer as the building block of these other models, okay? For instance, I'm gonna tell you the solutions, but I'm not gonna tell you exactly how we solve them, but you have hope. So for just perceptible differences, right? We use binary relations, but we augmented it with some threshold, right? So we now say, look, I'm gonna declare yellow number 1 better than yellow number 2 whenever now I introduce an intensity measure. So now I will declare better only if the difference between them both in terms of utility is larger than a threshold, right? So you can kind of extend the utility by means of this cardinality dimension with a threshold of perception. So you can model perception directly. So you can use the utility model there. So you still have kind of transitive and complete, but with this additional layer that allows you to get these shades, okay? For inattention or perception, well, you still keep the transitive and complete model, but you add an additional layer, which is the attention layer. So you add another dimension. So on top of rational and complete preferences, you add also an attention filter. So now consumer is two things, a preference relation and an attention filter, okay? That's a new development that we're gonna check in this class later, but that's the solution. So we enhance the transitive and complete model. For framing effects, well, for framing effects, you actually have to, again, model attention. So you have to model the frame, right? So you, for instance, you model search, and now choices will depend, for instance, on the list in Amazon, the searches in Google. So you will actually, instead of just describing the menu, I will also give you the position in the list. So usually the solutions for framing effects is enhancing the data. So instead of having this very poor data, just menus and choices, you have actually a menu, frame, choice, okay? And that's how we still have transitive and complete, but over the enhanced data. Got it? And then, social choice theory, collective choices is hard, but one solution that we're going to check in classes is the collective model. where pretty much you have each individual being rational, and we have some protocol for aggregation. And pretty much some of the rationality will still persist in some form. So we have to modify, of course, our model. It's no longer transitive, but it still has implications because it comes from transitive models, okay? So it's, you have an aggregation of transitive behavior, okay? Got it? So in the end, as you see, we are still going to use this model that we're studying today as the building block. So don't despair, okay? And now I'm going to give you just this proposition that we proved in the summer, and I'm not going to prove again, and you can check the notes if you need to, is that a preference relation that is rational and transitive and complete can be represented by a utility function, even only if it's rational. So remember, the key idea was that if you are not complete, you actually cannot have a unique utility up to monotone transformations that represents the binary relation, right? If you are not transitive, the same, right? So both of them are important. So, and this goes two ways, right? So why I just stated finite, because that's the only proof we have done. Of course, this can be enhanced for infinite data, but at this stage, I don't mind. I am gonna deal only with preference relations this class. So I'm gonna leave it that there, but we're gonna come back to utility later, so remember that. Okay, so back to the weak axiom. But this time, we're gonna present the weak axiom of revealed preference in the most general way possible. So this one covers any possible data structure that you can imagine. It covers budget sets, it covers menus from experiments like lotteries, it can cover, you know, anything really, okay? And now I'm gonna tell you the version of the weak axiom for this general setup. So if for some menu in the collection of menus, you have two items, X and Y, that belong to the menu B, and you observe X inside the choices of out of B, then for any other menu in the observed data, such that again, X and Y are there, and Y now is also picked in the second menu, then this implies that X also must be in the second menu. Okay, it's a mouthful, right? So who got confused? I hope a lot of you got confused, but we're fine. We're gonna be fine because we have the tools of revealed preferences. So if you translate this to revealed preferences, very easy, very, very easy. So the first time I read this in Mascolel was, what? If I have to memorize this, this is crazy, right? This is like a tongue twister. It's very long, very weird, a lot of implications, a lot of assumptions, okay? And it is, it's a mouthful, but transform it into revealed preferences. It becomes extremely easy, okay? So I'm gonna introduce the language of revealed preferences, and they are as follows, okay? The symbol here with a capital D on top is called a direct revealed preference relation, right? We say A is in a direct revealed preference relation whenever A is in the choice correspondence of the menu V and small v is in that menu, capital V. So in words, very easy, right? If I observe in my experiment the subject choosing A whenever V is affordable to him or her, then he reveals to me directly that he likes A's better than B. Do you agree? Good, right? That's the Samuelson insight. Samuelson invented this. So cool and nice and direct, right? From choices, I can infer preferences, right? Preferences are not observed, are latent. I cannot see them. By means of observing choice, I can now elicit direct revelation of preferences, right? Be careful. These preferences may not come from rational behavior, right? This is just data. I am deciding to call it revealed preference. Doesn't mean that there is a utility, right? They have to satisfy some properties to be compatible with rationality. Understood? Okay, right now they are just a definition, just data. So second definition, we say A is directly and strictly revealed preferred to V. And the symbol is the strict preference revelation with a superscript D. Whenever A and B are in the menu B, capital V, and A is picked, but B is not picked, okay? So B must not be picked and A must be picked. So what is the difference with the first one? The first one allows for indifference, okay? So you have a choice correspondence when you pick A and B at the same time. The first definition applies, right? But the second doesn't. Do you understand? So imagine a menu where I offer one of you lottery 1, 2, and 3, okay? And the consumer picks lottery 1 and 2, okay? Then lottery 1 is in direct preference relation to lottery 2, and lottery 2 is in the direct preference relation with lottery 1, okay? Now imagine another menu where you have lottery 1 and 3, and I pick only lottery 1, and I don't pick lottery 3. Then lottery 1 is in a strict relation with lottery 3, okay? Because lottery 3 is not picked, okay? So that's the definition. Hope everyone got it. And the final one is indirect reveal preferences. So we never say indirect because it's kind of redundant, right? I'm gonna put it in a parenthesis. But this final relation, we say A is in indirect parenthesis, reveal preferred to B with a star. Whenever there is a sequence of items in the choice set, A1, A2, AN, such that A is directly preferred to A1, A1 to A2, A2 to ... AN, and AN is we will prefer directly to B, okay? So this is a cool inference that is deeper than the initial one by Samuelson, right? This is an indirect inference. So if I observe chains of you saying lottery 1 is better than lottery 2, lottery 2 is better than lottery 3, and lottery 3 is better than lottery 4, then I conclude that lottery 1 is better than lottery 4, okay? So this is a chain of direct revelations. Now they become an indirect revelation of preferences, okay?
This implies transitivity, right? For this
no, this is just data.
Just data, right?
Yeah. I observed the sequence of choices and I collected them and recorded them, okay? And this chain tells to me that A1 is better than B in the reveal preference relation. The key word here shown is the revelation of preferences. These are not models, these are data sets, okay? So this is just something I record, okay? Nothing else. I call it preferences because it's suggestive of something, but they are not really compatible with rationality just yet, okay? So now, what we're missing, of course, is properties. And the first property that we're studying is the warp, the weak axiom of reveal preference. And now, we can say it easy. If X is directly reveal preferred to Y, right? Then Y cannot be strictly reveal preferred to X. So in symbols, if X, squiggle dy, then not Y, strict squiggle dx, okay? So all this mouthful of before now is summarized in this simple formula. Got it? So the work wasn't that hard, right? It was actually easy because the moment I transform it to preference relations, the direct revelation is very easy to understand, okay? The work just requires that you are not changing your preferences, that you are not flipping your preferences, okay? Good. So right now we're studying rational models, right? And of course, the next step is to show that if you are rational, and pretty much the choices generated by these rational preferences, the C-star model, are going to satisfy the warp, okay? So if I take some menus and I give it to a rational consumer, these observed choices will satisfy the warp, okay? So warp is a property of data, okay? And if this data is generated by a rational model, then this data will satisfy warp, okay? Got it? Good, so let's prove it. Okay, so first thing, right, by common sense, in order to test warp, I need at least 2 menus, right? Because warp can only be violated if I present the subject in the experiment with at least 2 menus, okay? So I'm gonna take 2 menus, B and B prime. And I'm giving the subject the possibility of flipping. So I have to offer him in the two menus, or here, two items, the same items, X and Y. So it must be that X and Y are in the intersection of B and B prime. Got it? Okay. And then, I'm going to show that if this guy is rational, then the data set will satisfy work. So let's just start with the definition, right? If X belongs to the C star, remember what is the C star? The C star is the set of maximizers of the preference relation on that particular choice. So in particular, it means that no other item there is strictly preferred to X. Okay. No one is better. And then also Y is there. Okay. So then that means that X is in relation with Y and Y is in relation with X. But that's just the definition of equivalence, right? So the symmetric part of this preference relation. So X must be, by definition of rationality, the rational relation must be indifferent to Y. Everyone with me? Okay. So in the world of rational consumers, if two items are in the choice correspondence, at the very top, they must be tied. So all of them are as good, right? All of them are tied in the top rank. So these are all the guys that are tied for the first place, okay? So X and Y are therefore indifferent to each other. The consumer is indifferent between X and Y. Now, let's go to the second menu, okay? And what was the statement in the second menu is that imagine there that Y was there, right? So if Y is there, then the work requires that X is also there, okay? Right? So then the only thing I have to check is that X is in there. So I'm gonna check that. So X is in the second menu because X is weakly better than B for all B, given that Y is better than all V in this menu B prime. And by indifference and by transitivity, it follows that X is also at the top. Got it? So two things going on. So the premise of work is that Y is in the second menu. Got it? So if Y is in the second menu, by rationality, it must be that Y is above all other items B in that menu. Got it? Okay. So now, because by the previous information, X is indifferent to Y, and X is also in B prime, then I know that X is indifferent to Y, and by transitivity, I know that this is weakly above every other item there, okay? So also in the top of the rank. So therefore, X must be in the choice correspondence in the second menu. Work is satisfied. Got it? Okay. So that's one way to prove it. I please at home try to prove it using just the direct preference relations. Way easier than this, right? This is using the original definition by Mascolel, and this is the proof in Mascolel. But if you use the preference relation language, it will be easier to prove it by contradiction, right? And that'll be easier. That's an exercise for you. Okay. So
sorry, quick question. Yeah. So this is one-way relationship. So if there's a rational preference, then it satisfies warp. But just because it satisfies warp doesn't mean it's rational preference.
Great question. Right. So this only means that warp is a necessary condition. So that means it's a testable condition of my rational model. Great. Now, that doesn't mean that if I have a data set that satisfies warp, it will imply that my model, that my data can be generated completely by a rational model. It doesn't mean that. It only means that in particular configurations of data sets, okay? And we're gonna study this today. So again, so we say this preference rationalize C relative to B whenever these two items are the same for all menus. So I already explained this equivalence, just a reminder. Now, I'm gonna prove the following, which is answering partially what Tyson asked. So if I have a data set such that warp is satisfied, and importantly and crucially, my data set includes all subsets of the grand choice set X up to 3 elements. So this one includes all tuples and all triples, right? So in a finite experiment, this can be, seems easy, right? Because you have 4 menus here. So all tuples, 3, and the triple. So four particular menus. But imagine your choice set is now size 100, 1,000, right? This is actually really rich data. And in fact, we call this rich data set, okay? So sometimes it's impossible to get it. But if you manage to get it, then there is a neat result. Work is enough or in fact sufficient for rationality, okay? But since I studied Mas-Colel, I learned something, right? And I realized that a key assumption here that Mas-Colel doesn't state explicitly, that is crucial for this result to hold, is that we are assuming that the choice correspondence is always non-empty. Okay, so I said something weird. So choice correspondence non-empty shouldn't always be non-empty. So let's go back to my experiment, right? So now I asked Brice, okay? So Brice, do you like, what do you like better? So do you like a Ford SUV versus a Tesla SUV versus a Porsche SUV? And you have to pick now, right?
First one.
So he's quick, right? But some people will say, look, I don't want to decide now, right? So if you're giving me the choice, I may want to do some research, and I may want to know which one is better, right? So for me, maybe one is more expensive maintenance. So there are a lot of factors. A lot of people will say, I don't want to choose now. They will defer this choice. They will not choose. Okay, so a key assumption I was making along this class is that the subject is forced to choose. So in an experiment, you can force the subjects to choose, right? To the extent that the ethics review board let you. But in general, that's usually not an issue. You force them to choose. But in real life, can I force Brice to choose? So if he goes, to the dealership, he may not choose that day. He may want to think more, right? That's an issue, right? A lot of people go many times to a shop and check many times the cars until they are decided. So being decided is hard, right? So not everyone is as decisive as Brice, right? So the possibility of not deciding is empirically real. It is real, right? It's important. And turns out that assuming that a choice correspondence is always not empty, as Mas-Colel does, is actually requiring a lot. Is actually ruling out a lot of behavior that will actually mind the gap between work and rationality. So what I'm telling you is that this result in Mas-Colel is not only assuming that you have this rich data set of all tuples and triples, but also that this particular experiment, the subject somehow is decisive enough that will always pick something out of tuples and triples. Do you get it? So if this subject is undecisive, then, the subject will not be covered by this term. Okay, so now, just to put things in perspective, let's go back to the Condorcet paradox. So before that, what I want to prove, I just want you to remember, right, is that rationality implies work. That we already know. But more importantly now, we're going to prove the other direction, that work implies rationality, but only under very special circumstances. You have all tuples and triples, right, a lot of data, but on top, your choice correspondence is always non-empty, okay? That's also important, okay? Now, let's understand why that's important. So let's go back to the example with the Condorcet cycle, okay? So I'm gonna go to this family and tell them, look, you won a contest, right? But you must decide now. So the contest is that you can pick tickets for any of these 3 events, okay? This is the menu. Now, this is the choice correspondence of the family. And I'm gonna ask you all to tell me what the family is gonna choose for winning, because they won this contest, right, by luck, and now they have to pick the the best item in this menu. What they will pick? Can you tell me? So they run majority, right? So they go item by item. They did this thing, and now the preferences that are listed are this thing, O-R-I-O.
I think I.
No, but according to these preferences.
Is it empty? You can't make a choice?
You can make a choice, right? That was the point, right? Right. So that was the spoiler alert, right? So you have a cycle, right? You keep going in circles, right? It's like Brexit. Do we get out or not, right? So circles, right? So this is a reality, right? So people sometimes get in circles, right? You cannot decide. Get it? So these guys will say, oh, wow, we cannot make a decision. So they say, oh, you lose your price. No? Eventually, you know, people will find a way to do it. And that's the interesting thing, right? How people get out of indecisiveness. We understand very little about that. But the important thing is that actually the theorem by Mascolel, the one I'm going to prove, only works if I'm ruling out these situations, right? So the moment you say you always pick something out of choices, you are ruling out certain kind of cycles, you see? So this is a very, you know, loaded theorem. We're assuming a lot, okay? So now let's go back to this and let's prove.
Sorry, Professor.
Yep.
Please, are you going to do 2 hours today or?
Can you say it again?
In 2 hours, the class is today is 2 hours or 1:30.
Ah, yeah. Sorry, I got. Thanks, Brice. So yeah, of course we're done. Let me stop it. Feel free to stop me next time. You know, you get too involved into this, so it's fine. Just tell me it's time. Good work, Brice. So yeah, you're free to go. And then, you know, any questions you have in the Slack. Okay, I'm gonna be here for 15 minutes more.
Okay, hello, Professor. I may have missed this in the beginning, but where would you post your syllabus and the notes? I may have missed.
So you're already in the Slack.
Okay.
Yeah, so I put 2 links. So one is the GitHub, so it's the BHAYAR, my last name, microeconomics 1. So this is this repository where you can download the zip with all the materials of the class. And this will be updated continuously, right?
Okay, thank you.
So just learn to use GitHub. It's very easy and convenient. Yeah, so that has the everything, okay?
Victor, I have a question.
Yeah.
So when you're giving like the Amazon example, like how people shop on Amazon, can it be like your choice is dependent on what other people choose before? Because before, usually, you know, when we go to Amazon, we see like, you know, who has bought which item more, you know?
Yeah.
So your choice is actually being determined by what other people chose before you, right?
Yeah. I mean, another example is, you know, fashion or just keeping up with the Joneses, right? So there are many examples of peer effects. Yeah, so that's another example of why intransitivity may happen. Of course, that's an issue about observability. So if you see the network of choices and you have some model of how consideration and preferences are, actually consideration, attention. The good thing about the new behavioral econ is that somehow we keep preferences the same, so transitive and complete, but we model attention. So for instance, the way people are modeling now peer effects is by means of how your network, the people around you will shape the consideration set. So in the case you're saying, right, is by means almost of an algorithm, which is a new source, but this is not well understood. So I would say, yes, of course, it matters. The way people are learning how to model this dependence of your choices on previous choices of other people is not really well studied. So this is really a new avenue of research. Yeah. But yeah, of course that matters. Nail has a paper about peer effects and how they affect choice consideration sets formation. And so that's kind of one of the very first papers doing that, right? But very few is done on that, really. It's hard to model. Yeah.
Victor, I have a question.
Sure.
Please turn to the order theory parts. I just want to ask why partial orders was of the existence of equivalence relations. What will it mean?
Which
in the
you
chapter
can,
1,
you can also share a screen, I think. I think you can share a screen, right?
okay.
You're talking about how the partial order rules out equivalence relation?
Yes.
Yeah. So yeah, I got an email about that, so I will clarify it. So the partial order, we have this, we pretty much are telling you that we have this strict relation, except for the diagonal, right? So we have all items are reflexive with each other, right? So modulo the diagonal, you're ruling out that. So if that's what you mean, I'm gonna clarify it in the notes because I got another email about that as well. But so in general, remember partial ordering is reflexive, so therefore it includes the diagonal, right? So every x is in relation with itself. But modulo that it rules out the indifference relation. So that's what I mean. Of course, it includes the diagonal because by construction we can add this diagonal. Usually, the diagonal doesn't do much. It's just easier to write choice correspondences using the diagonal than not. Because if I don't have the diagonal, so the reflexive with respect to itself, then I have to write, you are at the top, you're better than any other item that is not the same item, right? So just writing the choice correspondence gets longer. But, you know, this is just a mathematical convention. So in that sense, you know, the diagonal doesn't matter much for what we're trying to model. Yeah, but it wasn't an informal statement, so I would clarify. Yeah.
Okay. And another question is that in chapter 1, you said that the partial order can represent strict preference, but I think we should change the anti-symmetric to asymmetric, just like what you showed.
Yeah, in one version of this it was changed, but yes, so maybe it wasn't changed on this one, so I'm gonna find it and correct it, okay?
Okay, that's all my questions. Thank you.
Thanks.
I have a question.
Yes.
So regarding Condorcet case, you said the family cannot choose or pick up the best one, but what about they choosing all of them, like all opera and rock and?
Yeah, so that's so when trying to make people decisive, so there are many ways you can close the model, right? So one way that is famous in social choice is that you do the top cycle, right? So this is the elements at the top, they're in a cycle and there is nothing dominating them. So that's a solution. I think mathematically that's attractive. In real life, I don't know how attractive that is to model real behavior. One way that people do it in practice, people in not theory, but IO, industrial organization or experimental, is the presence of a default alternative. So you always have a choice that is outside the choice set. In particular for this household, it may be staying at home watching Netflix, right? So this is not in the choice set, but of course it's always there. So the default is staying at home. So in that case, you can augment the initial choice set with the default alternative. And then whenever empty, you default, you go to the default option. And another one, you know, more modern decision theory is that you say, okay, I cannot decide, maybe I will randomize, right? So maybe, you know, and that's, I think, more realistic because a lot of people will say, you know, we still want to make use of the winning ticket, right? So what do? Let's leave it to chance, right? And then you have a tie break. It's not even tie breaking, but it's you let, in this case, a dice maybe decide, right? So again, I think, you know, thinking about decisiveness and how to break this situation is hard and is actually not well studied. But I'm telling you kind of three possible solutions. So the top cycle is mathematicians have done it. I don't think it's that motivated by empirics. The default, I think, is realistic in some situations. And then randomization is, I think, is very exciting, but also it's kind of a little bit too flexible because it's kind of, how do you randomize, right? Uniformly, you know, you introduce another huge dimensional parameter. So it's kind of hard to choose, right? But yeah, so I think that's a good idea. So the top cycles is one. Yeah.
Okay, thank you.
Okay. Okay. That's it.